Good afternoon, YouTubers. If you love steam engine, you are in the right place. Which I happen to work time to time with steam engines. Love the way they work and how valuable they were for our history of mankind during the development. So I would say it's kind of a pity that we are not going through that anymore. Although there's some intent to get this back in some fashion, one way or another. But it's good. It's good to know how they work. And if you are, like, for example, a mechanical engineer or a chemical engineer, I mean, it's a must that you try to get this, as to understand this kind of principle behind this type of equipment, and for in general. So basically, I'm here. Here I am putting together a steam engine, and a very simple one, in where you have what would I call a single stroke piston engine, shown here on this side, and here's the valve. How I put this together, no plan whatsoever. There's no blueprints. I go by the blue. And basically, the first thing that you need to understand is what's the size of the piston that you want. So I went through, let's say that it's gonna be 1 inch, and from there you design everything else. That's kind of the beauty of this. So the only thing that I determine here is the size of the piston and the stroke. Those are the two most important. I would say for me, the two most important aspect is those two. Now let's take a look just for dimension wise what this looks like, and so let me show you how this looks like when you get some of that in drawing. I'm not doing the drawing of every part here. I'm only saying that this is basically a general dimension that I'm kind of following here. It's in a table of 300 by 300 millimeters, and you can see here the size of the flywheel is about 80 millimeters, the diameter. The true is said are 12.70. That's the radius, so the diameter of this would be about 1 inch. And so the valve. The idea behind this kind of a setup is that I want to have, if I go back again 1 second to my here, as you can see, these are kind of copper or brass fittings, because I'm gonna put live steam into this engine. Although all the part, basically everything else, gonna be PLA 3D printed. I want to preserve some, give some sanity to this design, basically using some brass or copper pipe here, just to ensure that at least the diameter of the either of the piston or the valve, the integrity will stay even if I use it for a long time under the steam, very low pressure steam. Basically, that's what I'm saying. And as you can see here, you can see that there's gonna be kind of a hose connection between the exit of the cylinder from the valve into the power piston. So this is the connection that I'm gonna be using. Again, everything was designed in Solidworks, very straightforward, no fancy of calling any fancy stuff from Solidworks. No, very simple, not a big deal. Regular, as you can see here. Basically, the most complicated aspect, if any, here, let's see where it might be here. I don't see anything complicated, except if you want to say there is something complicated, maybe the sweep might be a little bit complicated. The sweep that I did, which include, as you can see, a 3D sketch and a sketch. A sketch just to get the circle here, and this 3D sketch is just to get the dimension of the pipe the way I want it, the curves and everything. So I would say those are the two things, the most critical aspect of this design. I mean, difficult, not that they're very critical, but kind of you have to know a little bit about it, how to use them, so that this get oriented properly. Now, and obviously at the end of everything that you have put together, again, this is a rock solid, like it's nothing move here, because I put this in Solidworks on the for part. First of all, everything here, if it's gonna be a part, you have to be sure that when you do extrusion and things of that nature, like for example, let's see, this is identify the cylinder for the valve. If I check that out, and you will see in a second why I'm going through that. You see the merge result is not highlighted. That's important because eventually what's going to happen is when you do the merge, when you do the destruction will not be merged to anybody, to nobody. So that will preserve that as a solid piece, which is important too, and that solid piece will be identified here. Like for example, cylinder. With what cylinder? The cylinder for the piston, for the power piston, the piston crank. That's this guy here. Let's see, move this way here. That's right there, piston crank. The shaft, what shaft? This one here. The piston rod, this guy here. The piston, the power piston. See that guy there, and the valve crank is this guy here. Now the valve crank was the last, I would say, I think that it was the last piece that I put together here. Well, now actually, was the last part was this, the rod for the valve crank, and I tell you why. The valve crank, the valve is right here, the valve, the flywheel, the valve cylinder, and the base, where you want to have a base that everything fit, and eventually the valve rod, and it's right there. The valve crank is important because this is the timing. This is the timing for everything. I mean, if this is screwed up, I did one design originally on this. This is kind of a Rev 2 or whatever. On Rev 1, it was too long and I didn't like it, so I kind of cut it off a little bit more. And now it's to a point that I think that it will work okay. And but that's the part. How you know that it will work? For that, the nice thing is that you can take all these parts, all of them, and make them like this. Like you go here and insert into a new part. I'm not gonna do that now because I already did. But when you do that, what's gonna happen is that that new part is totally available for your assembling, and that's the important thing, that you want to take all those parts and make an assembling out of them. And I don't want to waste too much time on this, but I already did that, so I want to show you in how that will look like right here. And there we go, here we are. Here is the assembling part for the system, and I'm the view. Let me put the view back again, the view that you are used to. This is the normal view when you have everything put together. And the nice thing is when you do the assembling and put all the conditions, required conditions, how the things will work and what need to be tied to what, and you end up with all this good. Now you can move your your stuff, and it will look more like the way it should be, like a steam engine. And this is where you will try to check whether your valve design is doing what it's supposed to, because the idea is that steam will go through here, through this valve with the proper timing, so that when the piston is all the way down, like for example now it's all the way down, steam has to go in. Now steam need to go in and push the piston out, and eventually when the piston is going down, the valve need to allow, and you can see there's a hole there. As I move this, that hole will become more and more available because this piston is coming down, and the air or the steam trap here will go through and it will escape right through here. And that's the main idea of this design. Now the main point here, how about if we see that really happening? And to do that, you can do two things here in the assembling area of Solidworks. For that, it's kind of nice to do kind of a wire look into it, because now you can see, for example, you can see the valve. This is the valve. There's a gap within the valve that will allow, for example, right now steam cannot get in anywhere here, and because it's locked, you see the valve is in that position and The only way that steam will get in if I turn this way. Eventually, let's see, whoop, this way a little bit more. Sometimes hard to well, maybe sometimes it's better this way here. And now you can see how steam align, everything align, and now the piston is going up until certain point, and then I have still steam going on, you know, full steam until I want to go down. When I go down into this, like now, let's see if I move this way. You see now what you're gonna have actually is this way. No, I turned it the wrong way. It's this way. Here we go. Now it's important because the flywheel only need to turn one way, and that's the correct way. And let's see, it need to go this way. There we go. As the piston go down, the piston is at the bottom, and this is getting aligned to push the piston up with a lot of steam. Let's see, grab it through here. There we go. And now more aligned, more steam going in. Now we have the direct line, full steam ahead. And let's turn it a little bit more. Let's see which one should I grab to make life easier. And I think might be let's do one thing. It's a lot easier, you know, sometimes doing by hand. It's a little bit give you an idea, but the best idea is let's put this like this. Let's do the model like that. And let's get the model into a point that everything is kind of aligned. Let's see if I can align it properly here. There we go. Perfect. Everything's well aligned. I can see that steam going through, in, and therefore this guy need to turn that way. That's the correct way. Align this again. There we go. It's well aligned. Now let's do a motion study, and actually let's do create new motion study. And I have the proper orientation of this, and let's do a motor. Let's add a motor. I'm gonna add a motor, and the motor will be added to this guy, to the flywheel, and it's turning that way. That looks good. And what would be the good speed to analyze this? How about very slow speed, 3 RPM? 3 RPM, that will do. Now let's say okay. For how long we gonna analyze this? Actually, let's analyze this by let's see, 150. That will do. And let's do a playback loop, and I think that will look good. And now we will be able to analyze this and see whether the rotation is right. Yeah, it looks perfect. Now there we go. Now we can talk about it. How can we understand if this is working right? Right now the piston is coming down and air is coming through this way, or steam in this case. Now everything's locked, and the piston go to the bottom, and now I have steam. I can see that you see now the piston is still going up, and I close the valve, but now the piston is coming down. It's gonna work the way it is right now. It's gonna work perfect. If I put everything together the way it is here, it will work. I will say that I feel the valve crankshaft can be shorter. It is an eccentric type of crank design, so it has to be a slightly bit shorter than whatever it is right now, because I can see the idea will be to stay fully open there, right there, and don't move anymore, but it's moving it just a little bit. And now it's closing as the pistons go up to the bottom, and now it's trying to it opens to allow steam to go out. So it will work, no question that it will work. The way it is right now, it will work, but it would be better if this stay right there and don't move anymore. That's the plan. And then don't move. For example, it's also moving too much down here. There, see, it will just stay there, but it's moving a little bit more. So, but it's kind of nice because you can tell that the system will work the way it is. Again, the centric valve was designed based on this gap, on this aperture of this diameter, which is going to be 0.25 of an inch, or a quarter of an inch, and everything was designed with that in mind. Like for example, this valve here was designed with that cutoff of about the distance between this wall and this wall is about a quarter of an inch, and the thickness of this is also about a quarter of an inch. And with that in mind, you can design then the crank to be a half about those three values, which will be about 0.75 of an inch divided by 2, and that will be the eccentric that you need here. But again, you have other millimeter here and there that you are not counting for that, and that causes this a little bit of misalignment right at the end, but it can be corrected. Now that I see it, next time I will correct it and get this right to stop right there. That's the maximum that I want of that valve to move and stop. It needs to stop also right there, end of it. Shouldn't, this little gap there shouldn't be there, and that we can fix that up, no problem there. So, but it looks good, it looks perfect, it will work. And so I can put this back there, and you can see change perhaps to this design, so you see when you see it, or you don't, that hole back there. It's a little bit hard to see because of the flashing of the system, but right now you don't see it. It's pretty much getting over here to the time that I put, and it will start again. So that's basically it, not much into it. And again, this design basically is gonna be PLA, kind of everything will be 3D printed, but I mean most of it, except the part that I definitely will be subjected to a lot of steam, and they need to be kind of a bit fed up. That's why the cylinder and the valve are thick. I'm using basically an inch of material just to make them in diameter, just to avoid them to getting all messed up during the run. And the other thing that I'm not doing, maybe next time I will, is to put ball bearing right here. I'm not using any ball bearing between the shaft holder and the crank. I'm not doing much of that. It's just for testing, to get this going. But it's kind of nice. So again, basically the main point here with Solidworks, if I stop this, is just to do when you want to work on this, I did everything right there. That's what I did. Let's see if we get it right. Yeah, I did everything. Let me get these planes out so they don't bother me. Plane 4. There we go. So when you do that, when you have an idea, particularly is the stroke and how much of a diameter, the piston diameter you want. Remember, stroke and diameter, eventually the only thing missing is RPM. RPM, how fast you want to do this will determine the horsepower of this type of engine. But in the meantime, I'm not even talking about that, because I just want something that can hold together while I'm using very low pressure steam. I'm not using high pressure steam at all. But the idea is that you put together everything based on those two parameters: stroke and piston diameter. And after that, you put everything together. I can start, like every part here, where we are in the 11 bodies here. Every part here needs to be then exported so that you can have it when you are designing and put together, you assembling, like right where we are, steam engine auto recover, right here. I believe this is the guy. Yeah, right there. And this is on. Yeah, I got all the part here fixed. Check it out. Some of the part, like for example, the base is fixed. I also fixed some of the cylinder. Some of the part were kind of fixed, just because it makes a lot of sense when they are not moving. But so that's the idea. Let's see where we are. I'm in motion study 2. Let's go back to model, and here we are. So it's kind of nice that you can move it yourself, but to do kind of analysis of this valve, it's kind of nice to see what's going on with the, so you change here to wire just to see how things align or they don't, and that they properly do. For example, I'm turning this wheel, I was clockwise. Clockwise will not make any sense at all. In fact, it will never turn clockwise. And you know why? Because if I turn in this guy, let's get it a little bit. When I'm turning that guy, let's see if I can grab it here. You see, if I'm turning this guy that way, you see the piston is going down, but now you have steam going in. That cannot happen. So it cannot turn. It cannot turn. The guy cannot turn clockwise like this. It will not work. You see, that's the best way to. I grab it by the right place here, and it makes a lot of sense. You can see it that it will not work because the piston is going down, but steam is getting in, and that is not going to work. This guy will not be going down while steam is going in. So it has to turn the other way. Let's see if I can grab it somewhere here. Maybe. Let's see, can I grab it here? Let's see if I can grab it right there. Now, if I do what I'm doing now, oh yes, it will work. So is this the way I put it together on the assembly line? And that depends again on this. You see that I did the shaft kind of square to make life easier, because this guy, the crank, the valve crank has to be 90 degree different with the piston, with the power piston. And in the way I put it together now, that's the way it is, but end up being this guy turning. Let's see if I can get this, grab it somewhere here. Sometimes it's kind of hard to grab it. You need to grab it somewhere that makes life easier for you to turn it. I think it was this way. Let's see if I can do it this way. All right, perfect. Good alignment there. I'm going counterclockwise. Now I need steam to go out, and it's perfect. Steam will go out. That's the hard part. You don't want this to be jumping while you're doing this study. So, like for example, right now steam is going in, pushing the piston up to a certain point. Steam is slack. Now piston is going down, but then you need to allow the steam to go to escape, and that's perfect. So this guy needs to turn, as I said, counterclockwise, and that's what you see here in motion study 2. If I start this back again, and let's see where we are. There we are. It's turning counterclockwise, turning this way. You can see how nicely then things align. And now prepare compared to power piston going up, there, steam going up, pushing that piston up to the top, locking the steam now. Bingo, steam is locked. Now steam can escape right through this gap, which is half of the valve here. That's what the valve is kind of had, this kind of a cutoff to allow steam to go up. Well, I hope that this gives you an idea what you can do with Solidworks. It's kind of fun just to get this, get this done and have a good idea how the mechanism work on this particular case, and how can you optimize, like for example, this valve. Right now, one of the things that I can realize and I can tell you that basically there's steam on all the way from the bottom to the top. That's not good. That means it's going to be wasting a lot of steam. The steam is not expanding. The way I designed this crank valve here, the centric, it needs to cut off earlier. The steam had to be cut off earlier. Not much steam, and it's getting pretty much all the way. So perhaps one design will require me to modify this eccentric so that steam just get in, like for example right here. And let's take a look here. As the piston go up, there, cut off. You cut it off and you let the piston going, to expand, and now need to escape. So the idea is that can you adjust the cutoff of this valve, the steam. It's kind of hard with this design, but it can be done. I mean, we can modify the crank valve and use different sizes so that I can do that. Like for example, I want a cutoff right there, bingo, and that very little steam will be used because it will be expanded as it goes. Obviously, there's not enough. I mean, you don't have a lot of force while doing that, but you economize. I mean, you go through some process to reduce the amount of steam being used. But right now it's full steam. You can see it's full steam all the way up to the top pretty much, and now it's kind of close the steam because it's going to allow the steam here to escape. And so I don't think that I have to say anything else. Basically, let's stop here and going back here to Solidworks, and this come out basically from my work. I mean, this dimension, I don't put anything together here except that this is designed, for example, by the drawings available within the Solidworks based on the part that you have, and then you identify what you really want from here, like what dimension you are looking for to get this going, like for example smaller dimension. Let's see where we're here, and I decide that I want to be sure what's the size of these, like for example here, and I got the idea. That's it, 30, about 30, and actually let me take it from here. There we go, and that's 30. You see, and I got that dimension. If I want to know anything else, I can identify what it is. Like for example, these holes, what they are. 5.22, about 10 millimeters, a little bit the diameter. So that's basically it. No more to it. Like for example, I don't know. I think I got everything that I would like to know, just to get you so that you can have an idea of the basic behind here. Next video, I will show you how to go from here, which is the solid parts put together in a way that it looks like a steam engine, but they don't move at all. I mean, this is rock solid. And it's done just to ensure, because I don't have any clue of the design except for only 2 dimensions. With this model I started, I only had 2 dimensions, which was the stroke that I want to have and the diameter. The stroke here, if I remember right, was about 1 inch. I think that was the stroke, about 1 inch. And the diameter of the piston was about 1 inch as well. That's it. And from there, everything else was put together. Kind of a magic, huh? Isn't it? Then I have that. The next, so you identify all these parts, put it together. Then you go to assembling, and in assembling, you go right here. And from there, you stop this. Actually, let's go to model, and that's it. And you are right there. And we change the way this looks like about here. Obviously that doesn't add much because I want to see the inside of the whatever I'm doing. You can see the valve and the piston and everything, but definitely the idea is to see more this, so you know that the piston what it's doing versus the valve. And when you do that, you definitely get a very good insight that this will work the way it has been put together, so you don't waste material or time. And let's see what else. Put that back there so it looks pretty now, and that's basically it. As always, have fun, whatever be your final destination. God bless you. Bye.